Hello, I'm Niki Kaiser. I'm a chemistry teacher at Notre Dame High School, but I'm also the research lead there for the Norwich Research School, which is based at our school. And since January, I have been seconded part-time to the Education Endowment Foundation, the EEF, as their science content specialist. I'm talking today about some M's: metacognition, modelling and misconceptions, which I think should be relevant to any science teacher, although I'm a chemistry specialist. This tells the story of some ideas that I've been really interested in over a few years, and a little research project that I did with some support from the Chemistry Education Research Group from the Royal Society of Chemistry. I've been interested in these things called threshold concepts for a while, because I'm really interested in the way people think and why people understand things, but also, perhaps more importantly, why they don't understand some things. And so I was really intrigued by this idea of threshold concepts, which were described as this portal to a new or transformed understanding. I mean, that's amazing, isn't it? The idea that we have these fundamental concepts that once you've understood them, it transforms the way you look at things. And an example of this that I've seen people use is the idea of gravity. So if I'm holding this pen up and I tell you I'm going to let go my grip on the pen, then we would probably all expect it to drop, because the concept of gravity and the effect that it has on objects is something that has transformed the way we think. We wouldn't expect anything else to happen. So I was really interested in finding these concepts that transform the understanding of my students. And so these were described by Mayer and Land in 2003, and they were given certain characteristics: that they were transformative, that they are probably irreversible, and that they are potentially troublesome, those tricky concepts that sometimes take a while to understand. And this sounds really attractive. I mean, for me, this felt like, you know, those light bulb moments that you see happening in class sometimes, where you've been struggling and struggling to explain something, and your pupils have been struggling and struggling to understand something, and suddenly it clicks. And then isn't that just a wonderful moment when you're teaching? So I thought, well, if I can find these, then, you know, then that's what I'm wanting to do as a teacher. But I think there are some issues with these descriptions. First of all, the transformative nature. I think, you know, learning definitely is a liminal process, and maybe eventually this transformation, this light bulb moment happens. But learning, I think, is a series of kind of steps forward and steps backwards. And also sometimes you kind of get to the answer without actually understanding why you've got to that answer. Sometimes you just jump to there without actually mastering the concept, and it's known as mimicry. They call it mimicry in some of these papers about threshold concepts and so on. And actually and interest in this stemmed from a conversation that I had with a year 11 student a few years ago, when they were doing revision for an exam, and they were getting the answers right about all sorts of things, but it was really clear from a conversation with them that they didn't understand why they were getting the answers right. So they were answering questions about the structure and properties of ionic compounds, and yet from a conversation I realised they couldn't make the link between the structure and properties, and basically they thought that there were just two ions. If it was sodium chloride, for example, there were just two ions stuck together, and where did all this massive structure come from? And it turns out that she'd still kind of been stuck on this idea of these dot and cross diagrams that I'd introduced first to introduce the concept of ions, and hadn't quite managed to link the ideas together of the fact that this dot and cross diagram represented thousands, millions, billions of ions that then form this giant structure. And the irreversible idea is something I've become more and more, I found more and more problematic as time has gone on, because I do think sometimes we are able to kind of suppress or learn the right answer to something without actually changing our fundamental beliefs. So for example, when you see the sun appearing to rise in one side of the sky and then travel across the sky and set on the other side, do we really deep down think that that sun isn't moving around the earth? I mean, we know it doesn't, but do we really think that in that split second, you know, when we first consider things like that? And so I like the idea that Talanke talks about in this paper, which he talks about there being almost kind of steps that you take to get to the stage where you pass through that threshold to deeper understanding. And it doesn't necessarily just happen in one go, this kind of flip from not understanding to total understanding, and without review or looking back any reminders. However, I do agree that these are probably the troublesome, tricky ideas, and these are the ones that probably we want to do most with. But you know, nobody seems to have kind of defined what they are. So I'm beginning to think, you know, it's a good kind of concept, a good idea for thinking about teaching and thinking about the pedagogy behind what we do and the kind of way that we want to explain things. But this is an example of a page where people have written about threshold concepts, and for chemistry this is just a snapshot of them. I mean, there's all sorts of them out there, so where do we start? Another reason that they're so difficult to define sometimes is because it's very difficult to remember what it felt like to be a novice sometimes. So some of these concepts become second nature to us once we're familiar with them, and so going back to kind of retracing the steps, as it were, to what it was like when you didn't understand them is quite a difficult. It's an important thing, but it's quite a difficult thing to do sometimes as a teacher. So when I started being interested in these first, 4 or 5 years ago, I wanted to find a list. I wanted to find a list of threshold concepts that I could teach, and there just didn't seem to be one. So I started to look first of all at misconceptions, and being a chemist, I'm so lucky. There's some absolutely wonderful resources out there to help support with misconceptions. There's the Best Evidence Science Teaching. Royal Society of Chemistry has some amazing resources with questions about misconceptions. And Rosalind Driver's book is fabulous, and obviously I was working for a while on the science guidance report from the EEF, which has a lot of kind of useful stuff in it. But back then, the main source that I had was this RSC misconceptions resources. And I use these really as part of my teaching, really, reflective teaching. I was interested in using these diagnostic questions to try and uncover the understanding and misunderstandings of my pupils, but also, like with a kind of long-term head on, I was interested to see which of the resources which of the concepts they found most tricky. And it was really evident that there were certain concepts that were trickier than others. I often measured their confidence as well as their understanding of these concepts. And there were certain concepts around, especially around ionic bonding, that I realised my students found quite tricky to understand. And there were certain concepts, especially around ionic bonding, that you can see my students found quite difficult to understand. These were the ones that they were most unconfident about. And a lot of this stemmed back to the idea I'd come across before, that they were still thinking about these dot and cross diagrams. They were thinking of kind of monogamous ions, where one particular sodium ion would be forever associated with another chlorine ion. So it's very difficult then to kind of move on to this idea of ions that are just charged entities, and they are attracted to oppositely charged entities, and it doesn't matter how that ion formation came about in the first place. So at first this was really part of my reflective teaching. I think I changed the order of teaching. I started to talk about just ions in general first before I introduced dot and cross diagrams, so that was removed from the process of how we showed them forming. And there's some really good work done by Kate Nichols, if you are able to watch her talk, where she's then kind of taken this idea even further and kind of looked at ions and what I'm talking about later with the macroscopic and so on, and really talked about how and changed the way that she teaches these things. So really this was just something as a teacher that I was really interested in trying to help my students understand. I did have some data on this at the time because it was data I collected as a teacher, but it wasn't a research project, and for various reasons I wouldn't feel comfortable doing anything with that, you know, the kids weren't part of a research project. It was just something I was doing as a teacher to try and track their progress and their understanding and so on. So when the idea of a teacher researcher fellowship scheme from the Royal Society of Chemistry came about, I was really excited about this because I wanted to kind of look at this in a bit more detail, but make sure I'd got the ethics sorted out beforehand, make sure my students all knew that I was going to be looking at what they were doing and so on. And this is where the Royal Society of Chemistry scheme really helped me. I started from the beginning, thinking about ethics and methods and so on, and really began to dig into this a bit deeper. So my original research project, part of it was to look at conceptual understanding of my Year 12 chemistry group, particularly around bonding and ionic bonding, but a chance comment by Barry Ryan, one of my supervisors, meant that I actually surveyed adults as well as students, just to see what their understanding was right. And I have to say at this point, there's a hazard symbol there for a reason. This is just at the moment still very raw data. I'd started to look at it before kind of lockdown happened, when I just had no time to do this anymore. So it's still very much raw data. And I'm only presenting it as this at the moment, and I'm not expecting any, it's not robust or evaluated, it's just some initial kind of things that came out. But I managed to, I got a brilliant response from people, and I had 336 adults answer these questions, as well as my chemistry group. And about 180 of those were chemistry teachers, so there was a real mix there. About 105 were science teachers, but not chemistry specialists. And about 53 of them had chemistry A-level, so it was a really good mix. So certain questions were answered really well across the board. People knew that electrons moved in metals, and they were actually pretty good, possibly because of the wording in the question, but they knew that forces between molecules that were kind of being broken or overcome when chlorine became a gas. This one was definitely the worst answered question, but I think with hindsight I was kind of learning as I went along, and these were at the start, these were just questions that I'd always used with my students, so I hadn't been thinking about this from a robust evaluation point of view. And I think actually with hindsight this is a really badly worded question that I wouldn't have used again, so I don't know. I also had problems with these two questions and removed them in the end from the study. So what it did come down to in the end was my pet topic of ions and ionic bonding. What was really interesting though was that it flagged up some other issues with this. So for example, we talk about ionic bonding, but it's not a bond in the same sense that you have a covalent bond. So that kind of came up in a few of the questions, but basically the concepts that people have problems with is the idea that if we go back to our dot and cross diagram, people still found it quite difficult to remove that idea that there's a localized charge in the top right hand corner of a sodium ion, rather than a charge that's spread throughout the ion in all directions. And so the language and the localized ion idea and the idea that there are these monogamous ions that always stick together. They were three ideas that were quite tricky for people to kind of get past here. So what was quite interesting then was the difference in not just the answers, but the confidence of non-chemistry specialists compared to chemistry specialists. Perhaps that isn't surprising. You know, you're either, this is your subject and you're really confident with it, or it's slightly outside your comfort zone. And I must say again, this is raw data, but I'm just showing you some of the kind of trends and ideas. I looked at the right and wrong answers. So a green colour represents right answers, whereas a red or orange is a wrong answer. And then the depth of that colour basically represents how confident they were about that answer. So, you know, you can see that for these answers here that the chemistry specialists are not only getting the answers right, but they're quite confident about those answers, whereas, you know, sometimes we get a similar level of right and wrong answers for questions with the non-chemistry specialists, but they're less confident about it. So, you know, not entirely surprising, but these were quite fundamental ideas for, say, Key Stage 4 chemistry. And again, this is just raw data, but what was really interesting is when I kind of just looked at the significance of the difference and between chemist specialists and non-chemistry specialists. And even for fairly kind of straightforward ideas like this about ions being attracted to any ion, any other ion, the non-chemistry specialist science teachers, you know, there was a significant difference between their answers and the ones from the chemistry specialist science teachers. And what's also potentially interesting is that there wasn't any significant difference between the answers from the non-chemistry science teachers, non-chemistry specialist science teachers, and, for example, my year 12 set. So there's something that happens here, I think, between A-level and degree. You can see here the difference between people with A-level chemistry and a chemistry degree, that fundamental concept of ions just being attracted to each other or having a bond between them. There's a difference there. So this interests me not just because I'm interested in the stuff that we're teaching, but I'm really interested, like I say, in how we teach the stuff that we want to teach, how we help people understand things that they might not understand otherwise, what the best explanations are. So this for me all comes into this idea of pedagogical content knowledge. And this is one paper about PCK, pedagogical content knowledge, and they describe it as the knowledge about what to teach, how to teach it, how to engage students, and how to deal with students' learning difficulties. And it includes knowledge about students' misconceptions and the strategies to address these. And, you know, this is just good teaching, right? I mean, it's not just about knowing the stuff, it's about knowing the stuff about the stuff, how to teach the stuff, how to help people understand the stuff. And actually, if you look at the new ECF, the Early Careers Framework, there's quite a lot in there about kind of anticipating what these misconceptions might be, thinking about how to teach it, talking to other people that have taught these things before about the kind of hurdles that students come across all the time. It's a really kind of fundamental aspect of teaching. And, you know, this matters. There's a really interesting review by Vanessa Kind, and one of the studies she talks about is where pre-service teachers with varied science degree backgrounds often had very similar misconceptions to school students. And so quite often they repeated these misunderstandings within their own teaching. And I know that I'm certainly guilty of doing this. I mean, in chemistry, actually, let alone when I've been teaching biology or physics or things that are outside my subject specialism. So, you know, this is something that matters. And I think it also matters because, in my opinion, the best teachers are those that not only kind of know what the right answer is, but they're able to anticipate what likely wrong answers are going to be, and then they're able to plan around those. So you can see this study here where, you know, there's this idea that if you can identify common misconceptions you're more likely to help students progress and understand than if you just know what the correct answer is. You know, it's a really fundamental, important aspect of teaching. And so for me, this is, you know, the first aspect of where that little bit of reflective teaching I did at the beginning, looking at how my students responded to questions and the misconceptions they had. And once I began to understand what their misunderstandings were, I was able to change the way I taught, to change things around, to change the order of teaching, and anticipate things like the fact that they might forget that ions are attracted to any oppositely charged particle, that the charge is distributed throughout the ion and acting in all directions, and this idea that there's a 3D lattice with millions of ions, not just those 2 ions that they've drawn in the dot and cross diagrams, and also the fact that they remain ions, and they're still ions when you dissolve them in water and apply a voltage across them, and so on. So this helped me as a teacher. This knowledge beyond just the right answer really helped me as a teacher. But I do wonder if some of these ideas are particularly problematic in general because of the way we teach things, the kind of language that we use. And this isn't new, right? I mean, this is from a study by Keith Tabor and others in 2010. And he talks about the fact that students and teachers are describing electrostatic forces, but they are almost using language that's around directional bonds with kind of wires coming out of balls in atoms. And I do wonder how much of this comes from this pairing of ions where we teach the dot and cross diagrams in the first place. And, you know, another aspect of this that's really entrenched is this idea that ions are formed to gain a full outer shell, and so therefore ions must be more stable than atoms, and this octet rule is really kind of entrenched and can then kind of hamper later understanding. And actually I remember this is from an RSC diagnostic that I remember seeing on my PGCE course and getting it wrong. You know, it's a really, so don't be embarrassed if you did. It's a really tricky kind of idea. And, you know, this might explain the difference that I saw between people with and without a chemistry degree, because ultimately, you know, the octet rule and the stuff that we teach at GCSE and even A-level to a certain extent is a shortcut. And this is a really interesting article by David Reed in Education in Chemistry, if you ever get a chance to read it. And, you know, he argues that it does all come down to energetics, and maybe we should be kind of introducing some kind of caveats from the start. It's you can pause this and have a read to see what you think. But, you know, even then, does this matter really? Well, possibly yes, because it can set up misconceptions that are quite difficult to overcome later. And, you know, one of the first studies I showed from Stillman is about the fact that it's very difficult to kind of suppress ideas that we've built up over years. But also, you are less likely to have a subject specialist teacher in certain schools, schools that have, for example, a high proportion of pupils entitled to free school meals than in other schools. Now, that's not to say that people cannot teach out a subject specialism. It's just to say, you know, there is this difference sometimes in certain concepts potentially, and maybe that's more of an issue in some schools than others. Just switch the lights on. But ultimately it could be, it might not be that straightforward anyway. I mean, certainly there was some research that was carried out by the Edu Data Lab, and they found that having more specialist physics teachers didn't seem to increase physics results. Now, you know, in the short term, maybe it doesn't. I still think there's something about kind of short-term understanding and longer term. But, you know, I would argue that for example, this concept that I keep harping on about these kind of localized ions and the ions retaining their character even in solution and so on, which is something that you could probably get through GCSE without properly understanding, does become very important when you're trying to apply it to other ideas. To a certain extent at GCSE, but definitely at A level. I mean, just this one concept is important for structure and bonding in ionic compounds, but it's also really helpful to help you understand ionic equations, and not just the algorithm, but why they are used and what they represent. And actually, this was another really interesting example for me, where I was teaching my year 13s and we were using ionic equations, and they were solving them quite happily with an algorithm, but they said to me that they didn't really understand why they were crossing out some ions and not others, and leaving others in there. And it was only when I just happened to have some I've been doing precipitation reactions with my GCSE class, my year 11s that day. So I just kind of got them out and I showed them this precipitation reaction, and we kind of drew out the ions that were there at the start and the ions that were there at the end, and the ions that were in solution and the ones that had formed a solid and so on. And finally, you know, all of these kind of different ideas that they had kind of came together, and they could begin to understand why some of them were still basically unchanged at the end and from the start and so on, and this idea behind ionic equations. So I do think, yes, these fundamental ideas are important, and also obvious examples like, you know, solubility, why some things are soluble in certain solvents and not others. You know, we're talking about electrochemistry and so on. All of these ideas rely on a fundamental understanding of ions and how they behave in solution. So this is where my SERG research project came in, because I really wanted to find out if there was a way I could measure an improvement in conceptual understanding by using a particular framework in lessons. And the short answer is I didn't. Not a really kind of clear-cut improvement in conceptual understanding that I could measure with diagnostic questions, but a slightly different kind of level of understanding. So when I was talking here about my year 13s, one of the problems they had with understanding this was that they could understand the concept of ions in solution. They could understand the concept of the property of ionic solids. They understood precipitation reactions and how they work, and they had an algorithm for solving ionic equations, but they hadn't actually linked all of these ideas together. So they could observe things in the lab, they could do algorithms to solve ionic equations using symbols, and they had some kind of understanding of all the concepts behind them, but the putting it together was what they found tricky. But one of the fundamental threshold concepts that Talenke talks about in this paper here is the idea that we have to link conceptual levels together. And these were summarised by Johnstone. This is from a paper from 1991, where there's the idea of 3 conceptual levels in chemistry, linked by Johnstone's triangle. There's the macroscopic level, which is the stuff that we can see, the observations we make. Then there's the submicroscopic level, which is the things that we can't see, but explain those things that we see on the macroscopic level. So the way ions and atoms interact, for example. And then there's the symbolic level. So as chemists, we represent things with symbols and equations. And the point is that as chemists, we are quite happy with moving between these layers, these conceptual levels quite fluently. That's what makes us chemists. But the students that we teach probably aren't so fluent at doing this. And one thing that arises from this is that as chemists, we are able to link things that aren't very obviously linked on the surface, but we know that they are by things that we can't see. For example, all of these processes here, as a chemist, I know that they are linked together by the behavior of ions, and I know that I have different ways of representing them. I have kind of symbol equations, I have representations with for example, dot and cross diagrams, and there are different ways that they will manifest themselves, different observations I will see, but ultimately it comes down to the behaviour of ions and so on. The other thing that I know as a teacher is that a really powerful approach for pupils that comes really from the idea of metacognition is modelling your thinking. Not just, again, not just describing the thing, not just telling the students the answer, but describing how you get to that answer and why. And so when I read this paper in Education in Chemistry, or a description of this paper in Education in Chemistry, it really interested me, because what somebody was doing was taking this idea of Johnston's triangle, thinking about metacognition and the power of explicitly modelling your thinking and kind of putting them together. Basically, it talks about how a teacher said, you know, every time he introduced a new concept, he would say, let's triangulate, and they would literally kind of draw these or explain or... So the idea was that by explicitly pointing out the connections between these conceptual levels, by explicitly modelling your thinking as a teacher, students would be able to see the connections better themselves and link between things and between ideas. So I designed this worksheet with a bit of help from Oliver Caviglioli. Thank you, Oliver, who helped me make it a bit less cluttered and easier to work with. And the idea was to try and draw out this understanding from my students. And I found it useful on a couple of levels, actually. So first of all, when I was teaching things, I could get them to kind of draw their own ideas into it, and this helped me to diagnose any kind of misconceptions or things that they've missed there in the first place. But also it was really useful for seeing the different ways that different groups of pupils or pupils represented the same thing. And so, for example, I used this as a way of year 12 students collecting their ideas when we did a displacement ions practical. But with my year 10 students, once I'd done this with my year 12s and we talked through the different conceptual levels, I used this as a way of teaching displacement reactions, which also comes into year 10, and again they have to kind of look at these ions and equations and so on. But ultimately what I wanted to see was if this helped kind of deepen or develop my year 12's understanding. I don't think, as I say, I don't think I could do this in a nuanced way in enough depth with simple diagnostic questions, and I couldn't relate one to the other. So that side of things, no, I didn't do what I wanted to do, but I did develop it and use it in a number of lessons and found it a really useful kind of diagnostic tool for helping to draw out understanding and for kind of displaying things and explicitly kind of showing these ideas and the links between them when I was teaching. But I did conduct a couple of interviews with students to see if we could use it to draw out the differences as well as the connections between certain ideas. So, for example, you have a precipitation reaction here, and you have a displacement reaction here, and here this is just a simple saturated solution and crystals coming out of solution, and so we did kind of talk about the underlying principles there, but that's really, I didn't get as far as I wanted to with that, and I'll have to think about how to use that or what it tells me. So actually, as I say, one of the things I found it most useful for was as a teacher to kind of help me structure and support explanation. So this is some year 10s work that we were doing, and not just to support explanations, but kind of show the links between things. So, you know, on the one hand, we've been talking about ice melting here, and this is their sheets, and here we're talking about the idea of melting curves, and you know, there are ideas that link the two, and they began to kind of see the way these link together. Also here you've got the idea of sodium chloride again, ionic compounds, and the different ways that we talk about those. So, you know, with my year 10s, with me kind of directing the way they filled in the sheets, it was quite helpful, as well as the kind of diagnostic side, and letting students fill them in themselves. And, you know, then that meant that I could begin to get students to write about things using the sheets and draw out the explanations. There's also a really interesting app that's been developed by Sunflower Learning that specifically looks about linking these conceptual levels together, and because it's such a visual thing, and it's such an important thing to be able to link these together. So that's another kind of lovely thing that came out as I was kind of looking at these things. So where do I want to go with this? Well, I do have to really look at this data properly and see if there really is some value in looking at the comparison of different groups and concepts. And I also did a second lot of data where I really probed some of those sticky concepts a bit further. And again, I had a brilliant response, again, from science teachers. So I'm quite interested in like the way that we understand things and subject knowledge and so on. I'd like to look again at those interviews. I would love to do some further interviews. I'm wondering about kind of comparing the way that they talk about them with the way that experts talk about them, for example. And I'm really interested in looking at how others are using these kind of approaches as well. For example, Kate Nichols at City of Norwich School, again, another talk on Research Ed Norwich, explains the work that she's been doing there. But really, I need a lot of thank yous here. Suzanne Ferguson, Barry Ryan, who were my mentors for the SERG research project. David Reed, who wrote the original paper, article about the paper, the triangulation paper, and does loads of really interesting research summaries in education and chemistry. Michael Seary, who has just been such an encouragement with all of this and started the SERG programme in the first place. David Tim, who has set up the Sunflower Learning app, looking at these different conceptual levels, and Kate Nichols, who's doing the work at CNS, but also lots of other really lovely people. And if you want to follow up on any of the references, there's a copy of this PowerPoint at the bit.ly address here. And I've tried to make it quite clear what all the different references are throughout, but if you want any direct links to them, please do ask, and I will send them to you. Thank you.